Train a classifier that beats guessing fast. By the end, you will have a working logistic regression model. You will see how it compares to a simple majority baseline and how class weighting changes learning. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Logistic regression matters because it gives calibrated probabilities and usually improves accuracy, which measures the share of correct predictions. It is fast and memory efficient, but it assumes a linear boundary, so it can struggle on complex non-linear data. On small datasets, it often gives big wins over naive guessing. In practice, the trade-off is simplicity and interpretability versus modeling power for hard patterns. Intuitively, logistic regression draws a line or hyperplane that separates classes and converts distances to probabilities. It shines when classes are roughly separable with linear combinations of features. It does not automatically capture complex shapes unless you add features or transform inputs. We will build a tiny demo dataset, train logistic regression, compare to a dummy baseline, try class weighting, and run predictions so you see end-to-end. We will build a minimal binary dataset, train a logistic model, compare its accuracy to a most frequent baseline, try balanced classes, and finally, predict on new points. This snippet builds tiny labeled data and computes a simple majority class baseline. It creates a small feature list and matching labels to form a minimal binary dataset. The counter tool counts labels so we can pick the most common labels stored in MAJ. Accuracy appears here as the fraction of correct guesses, simply the number correct divided by the total. Predicting MAJ for every item gives a baseline score that any trained model should beat. The printed majority and accuracy give a concrete, easy-to-understand target to improve on in the next steps. Now we will train a logistic regression model on the toy points. This snippet trains a logistic regression model on the toy points using the liblinear solver. The model estimates weights that separate the two classes and stores the label order in the classes underscore attribute, which tells you which column of probabilities matches which label. The random state parameter forces the same result every run, which helps when you demo or debug. Changing the solver or using different regularization strength will change convergence behavior and the smoothness of the decision boundary. The printed classes confirm the model was set up for binary classification. Next, we will compare that trained model to a dummy most frequent predictor. This snippet compares logistic regression against a dummy most frequent baseline. The dummy classifier always predicts the most common label from the training data, mirroring the earlier baseline, but in a standard interface. Calling score on both the dummy and the logistic model computes mean accuracy on the same dataset. The Boolean better checks whether the logistic model's training accuracy exceeds the dummy baseline, which is a quick sanity check. If you reduce data or add noise later, that comparison can flip. A true value means the trained model learned more than a static guess. Now let's see how class weighting affects learning on imbalanced labels. This snippet adds class weighting to handle imbalance and checks for changes. The second logistic model uses class weight set to balanced, which makes rarer labels count more during training. We train it on the same examples and compare its training accuracy with the original model using a simple equality check. On a small, mostly separable set, both models often predict the same, so accuracy may not change. As imbalance rises, balanced weighting typically improves recall for the rare class. A true equality result indicates weighting did not change predictions on this toy set. Finally, we will run the model on new points to see live predictions. This snippet runs inference on new points to get final predictions. The new inputs are 3 simple coordinate pairs, chosen to reflect low and high feature sums, so you can judge how the model generalizes. Using the trained logistic model to call predict applies its learned weights and threshold to each example and returns labels. If you want finer control, you can use predict proba to get probabilities and then change the decision threshold to trade precision for recall. The printed labels show the classifier's decisions on unseen inputs and confirm the learned pattern. Recap: Logistic regression learns a simple linear decision rule and gives calibrated probabilities. Use it for fast, interpretable classification when features can linearly separate labels. Caveat: it struggles with complex nonlinear patterns without feature engineering. Next step: tune the regularization parameter on a validation split to see how model complexity affects accuracy and generalization. If learning AI foundations in Python helps you, subscribe and watch the AI Foundations videos.